Hello, everyone. My name is Jens Jasche. I'm a senior lecturer at Stockholm University in Sweden, and today I would like to tell you about building digital twins of the universe. And that's work where we basically can transform cosmology as classically done with summary statistics to reconstructing our actual universe. The idea is that we arrive at statistical models of the actual large-scale structure in the universe that mirror the actual distribution of matter in the universe in as much detail as possible, and that enables very concrete and interesting cosmology tests and understanding of physics. The work I'm going to present here has been done in collaboration with a lot of people and has been picked up by a lot of other groups, and it is picking up speed at the moment, and we are establishing it as a new alternative to cosmological and inference. In particular, the work I'm going to present has been done in collaboration with lots of researchers of the Aquila Consortium, and the Aquila Consortium is one of the international research collaborations which pushing forward the development and establishment of the field-level inference approach I'm going to talk here about. I just want to give you a very high-level motivation for what we are interested in doing. And in particular, we are interested in understanding our specific universe. We want to explain cosmic structure and the universe evolution. We want to be able to link our theory to the universe that we actually observe, and we want to be able to build predictive models constrained by these observations. And what you can see in the right here right now is the evolution of a typical cosmic large-scale structure from the beginning to the present. But what I'm showing you here in these final slices is that when overlaying the actual galaxies of the actual universe in red dots here, you see that these forward evolved dark matter distribution is representative for the actual universe. And that's what we mean by a digital twin. We want to have a computer physics model that reproduces the actual universe in as much detail as possible. And that's a departure from the classical approach of analyzing cosmology through summary statistics like 2-point or 3-point statistics. And summary statistics typically just test the consistency with typical ensemble realizations of the universe, but they miss out on the specificities of the concrete realization we are living in. As such, summary statistics provide a necessary but not a sufficient test to explain the actual universe as we observe today. So the fundamental limitations of this classical approach are that we observe unique structures in the actual universe realization, but summary statistics test only averages and are not very sensitive to the specifics of that. And because of that, they discard information unique to our universe. And throughout this presentation, I will show you that by accounting for the specific realization of our universe, we are enabling, first of all, using more data or information of the data, and also we are able to have more detailed tests of cosmology. The approach that we are developing and pushing forward is called field-level inference approach. It advances cosmology from just pure summary statistics of getting average understanding of the universe to a mechanistic explanation of 3D cosmic structures. We now want to have the full dynamic formation history of cosmic structures that explain the actual observations, ideally object by object. And throughout this presentation, I will show you how far we have come with this approach, and that it enables a lot of interesting things that can be done in the future. I want to use the following slides to give you a very high-level overview about what field-level inference in cosmology is and why it's an optimal approach to data analysis beyond summary statistics. I'll start with a little Bayesian interpretation of that, and within a Bayesian perspective, we can interpret cosmological data analysis in basically 3 tasks, like model selections. What is a world model M? This is gravity or alternative gravity models. We are tasked with parameter inferences. So once we have a specific model M, for instance, lambda CDM, what are its parameter values omega that are determining the evolution of this model or the universe under this model? And then finally, we would like to infer universe realization, that is, given a model M and parameters omega, what are the actual initial conditions of the universe that give rise to the actual observed meta distribution, the arrangements and orientations that we are actually seeing. These are the three questions that we can typically ask given the data, and we can ask these questions within a Bayesian context by just writing the joint posterior of the initial conditions X, the model parameters, and the model M given the data D. By using Bayes factorization, we can just factorize it as the first term is the posterior distribution of the model given the data. The second term is the posterior distribution of the initial conditions and the model parameters given the data and the model. And we can further factorize it into these three terms, with the first is the posterior of the model, the second one, the posterior of the model parameters, given model and the data, and the last one is the posterior of the initial conditions given the data, the model, and cosmological parameters. It's interesting that we can immediately read off what these questions actually answer. This is the first one is the question on the world model. The second one is a question on the average laws of the universe, like cosmic expansion, average density amplitudes, and velocity magnitudes. And the last term on the specific initial conditions realization asks question on the location, arrangement, direction, orientation, and alignment. So we see that these different terms ask very different questions about our universe. And while we can ask them all like that, currently cosmology asks mostly questions about the second factor here, but what we are trying to do is we try to answer questions jointly about the initial conditions and the cosmological parameters given a specific model like lambda CDM or alternative models that are available and the data. So the task that we try to address is to jointly infer cosmological parameters and the 3D realization of the universe to optimally explain the average behavior of our universe and how specific realizations and meta distributions of the universe came into being. And I want to illustrate this here today by applications to the nearby universe and even going to the application of the local group, the Milky Way Andromeda pair. So in order to address these problems within a fully Bayesian approach, we need to create a generative model for the cosmic posterior inference. So we start out with a prior on our cosmological parameters and also the three-dimensional initial conditions. We can then basically forward them through a physics model that solves an n-body gravitational simulation from the initial conditions to the present. And then we can turn the simulated outputs of these nonlinear gravitational evolution into an observation by using phenomenological galaxy biases models and use selection functions and so on. And we make a prediction for the actual observations, which we can then compare to actual data and see how well we actually reproduce the actual data and update our initial guesses. The actual physics forward model is much, much more complex in reality than just shown above. Since we are using a simulation-based framework, we can just simulate everything from ab initio, from initial conditions to the data by taking into account a variety of very complex aspects of the data generation process. That's first of all starting from the initial conditions to arrive at non-linearly evolved galaxy fields. We can then introduce velocity perturbations, redshift distortions, and cosmic expansion. And finally, we can also apply selection effects and likelihood to make predictions for the expected observations under such a model, which can then be compared to actual data. And we can use this data mismatch to update our guesses of the initial conditions and the cosmological parameters and iterate this framework to jointly infer cosmological parameters and initial conditions. This is feasible because we have a fully differentiable generative data model. In particular, we use the Borg algorithm, which has a fully differentiable cosmological simulator in there that allows us to propagate information from the final density field to the initial conditions and update initial guesses. We can basically implement this kind of framework into a standard Markov chain Monte Carlo approach, which guarantees a Bayesian inference through the long sample guarantees of the Markov chain Monte Carlo approach. The approach works by starting out with initial conditions. These are then forward evaluated through a physics simulator. We have some in-painting of traces like galaxy bias, redshift distortions, and light cone effects are accounted for, which is then led to a prediction of an observable. These are then compared to actual observations of data. Mostly we are dealing with galaxy clustering data, but we can also use other data. And the data mismatch through a likelihood evaluation is then used to update the initial conditions. And this framework is iterated through a Hamiltonian Monte Carlo approach with very efficient inference technique in high dimensional spaces. But as a result, we obtain a posterior distribution of the three-dimensional initial conditions, which can reproduce our actual data and cosmological parameters under the model that we are using here. Just to give you an idea, this is a reconstruction, an early reconstruction of the cosmic initial conditions, which we did from the 2M++ survey in 2019. And what you can see here is a reconstruction of the large-scale structure surrounding us and roughly at an epoch of 13.8 billion years ago. If I flip to the next slide, then you see if we evolve that forward in time, then we basically reproduce the actual large-scale structure surrounding us today. In black is the reconstruction of the dark matter distribution under the dynamical forward physics model. And in red dots, we overlay the actually observed galaxy distribution. And you can see that there is great spatial correspondence. And if I go back and forth and you look, for instance, in these regions here, then you actually see that these are the initial conditions which just have collapsed into the actual structures that we are observing today. So what I wanted to convince you of with here is that this technology allows us to basically get a physically plausible initial conditions explaining structure formation over 13.8 billion years and resulting in a representation of the actual universe that mirrors the actual cosmic large-scale structure surrounding us. This is a significant step forward from just a statistical characterization. It is not only a descriptive approach to cosmology, but it's a mechanistic explanation for how these structures came into being. And that's a transformative step forward into cosmological large-scale structure analyses. Obviously, we can use this technology to do the classical cosmology tasks, like we can use field-level inference to infer cosmological parameters. And one of the early pioneers of that was Natalia Porkeris, who extended the field-level inference approach towards analyzing weak lensing shear data within a hierarchical Bayesian model, where she starts out setting cosmological parameters and the initial conditions. She then evolves these large-scale structures forwards and even introduces baryonic feedback signal, then creates a tidal field in this pipeline and predicts observable for intrinsic alignment and reduced shear. And that basically results into the predicted shear that can then be compared to data at the field level at every individual position in space. And that allows a very detailed simultaneous reconstruction of the three-dimensional meta distribution and the cosmological parameters. The most important point that Natalia was able to demonstrate is that using a field level inference approach, we can extract much more information of the original data. So what you can see here in the left panels are the actual true initial conditions. In the middle panel, you see the ensemble mean reconstructed initial conditions. In the lower panels, you see the corresponding final density fields. So the importance is that the approach uses simultaneous reconstructions of the meta density and initial conditions, and also constrains cosmological parameters. In particular, in this test, Natalia performed analyses of sigma 8 and omega m constraints. In blue contours, you see the field level inference constraint, whereas in the orange contours, you see the typical two-point statistics analysis of the angular power spectrum for a similar analysis. And these tests indicate that we roughly get a factor of 3 to 5 improvement in cosmological parameter inferences when using the entirety of the three-dimensional field instead of summary statistics. This has been further demonstrated by a variety of other research groups. We have now seen tests on expansion dynamics by Cody Ramana. Andrews et al., they investigated reconstructions to constrain primordial non-Gaussianity, and we have Porcaris and others. And other groups also, as indicated here, have demonstrated that field level inference can improve over traditional methods by increasing the parameter constraints by factors 3 to 5. This is a significant improvement over the traditional summary statistics analyses, which we will be able to explore much more in the future. The technology is still at an early stage and is currently built into a state where we can basically use it robustly for actual data applications. It's an interesting study where this additional information comes from. And there have been a variety of different studies. One of these studies were recently done by Fabian Schmidt, and he was able to show that by using a field level inference approach, you basically systematically use all higher order endpoint functions, and it's only limited by the order of your physics forward simulator. So the more accuracy your physics forward simulator in the inference provides, the more it captures all higher endpoint statistics automatically, and you don't have to design anything manually by this. So this is one of the indicators where the actual information comes from, that it automatically uses all higher order statistics. But in addition, it is also a causal inference approach, and through the causal and physical internal consistency of the physics models comes additional constraints that allow for better and more detailed parameter constraints. So what we can see is that field level inference also excels at the traditional cosmological task of constraining cosmological parameters. But what I want to do here right now is I want to also show you that it comes with additional properties that we can use for testing and analyzing and understanding our actual universe. And in particular, I want to present to you the Manticore Local project, which is a digital twin of the local supervolume, roughly 300 megaparsecs surrounding us. And I want to show you the degree of detail and how much we can now use individual large-scale structures to test the predictions of the cosmological model and what kind of studies it might enable in the future. So why are we interested in reconstructing the nearby universe? The nearby universe consists a very interesting test for field level inference and cosmology in general for various reasons. It is the most nonlinear regime that we can observe because it's very close by on the light cone. So it's the large-scale structure that has had most time to evolve. At the same time, it's cosmic variance dominated because no cosmological averages are possible because we are below the scale of cosmic homogeneity. So this is a scenario where we actually have to account for the specific matter realization because we do not have sufficient volume for averaging. And this is very interesting. At the same time, we have rich observational constraints. There's lots of observations in the nearby universe that allows us to test nonlinear universe physics in various regions. And if it is not available, one can even think about getting such data on relatively short notice with smaller designed missions to do this. And finally, the nearby universe is of particular interest because of the observed cosmological tensions, in particular with respect to the Hubble tension. In order to constrain and reconstruct the actual universe surrounding us, we will be building upon the 2M++ galaxy catalog. And this is a galaxy compilation roughly covering data out to 200 megaparsecs surrounding us. What you can see here is the galaxy distribution. In the middle panel, you can see the survey footprint, and we have also the N of C distribution of the galaxy, so you get an idea about the data set. What we've been doing then is we have been using the Borg field level inference approach, applied this to this data set to get the initial conditions and reconstruct a posterior distribution of the cosmic large-scale structure surrounding us. And this is the result, what we can see here. This is a numerical representation of the posterior distribution of the meta distribution given the data, model, and cosmological parameters. The different realizations, the fluctuation structure is representative for the different realizations of the data constrained posterior distribution. In red dots, you see the overlaid galaxy distribution, and you see that our large-scale structure reconstructions represent the galaxies in very high detail. You can see that in regions where we have lots of data, the large-scale structure is very well constrained and mostly stable. The residual fluctuations that you can see here is the actual exploration of the posterior distribution still allowed by the uncertainty of the data. More interesting in regions like the zone of avoidance, where our Milky Way is, through which we can't look, and we don't have data, you see that the large-scale structure is fluctuating much, much more because we have less data constraints, and that allows to explore a larger space of the possible solutions for the large-scale structures surrounding us. But there are regions where you can see that the gravitational physics model allows us to extrapolate. For instance, here we see on average coherent and consistent large-scale structure connecting through the zone of avoidance. Similarly, here above, where we now see that there's a probabilistically and physically plausible representation of the cosmic large-scale structure constrained by the actual data. We can now see that the field level inference approach allows us to give a very detailed representation of the actual large-scale structure surrounding us, not only a statistical and probabilistic summary of it, but a very concrete realization in which we are living. We can test the plausibility under the physics model of this large-scale structure by using the classical cosmological tests like summary statistics. And what I'm showing you here is the meta-power spectrum for the volume that we are analyzing here, compared to a random simulation lambda CDM universe. In blue, you see our reconstructions including the uncertainties, and in orange you see the corresponding random numerical simulations, and you see that there is great correspondence down to the Nyquist frequency. Similarly, we see the behavior for the halo mass functions that are in agreement with the expectation of a lambda CDM model, and you can see that we are basically providing the same kind of information that you get from a classical analysis when you do a statistical summary analysis. Field level inference incorporates all this kind of information. But we can go significantly beyond that because we can study individual structures. And what I want to show you here is the degree of detail that we can actually account for right now. What you see here is the zoom in on the posterior distribution of the coma cluster. Coma cluster is a very known and very peculiar cluster that has been very well studied. What you can see here in these panels, these are 50 different realizations of the coma cluster allowed under the data. And in the upper right panel, you basically see the ensemble mean from our posterior distribution for the mass distribution in the coma cluster. It's very interesting what we can see here. So we can basically see that the coma cluster is the center of 3 to 4 inflowing filaments. And that's actually expected and very interesting because we know that the connectivity of the large K structure tells us something about the mass. And a cluster of the mass of coma is expected to have 3 to 4 filaments. And we can basically see that on the ensemble mean, we basically have these 3 to 4 filaments coming in. So apart from the typical cosmological analyses, we now also study individual objects like the coma cluster, its masses, its dynamics and properties under the cosmological large-scale structure formation model, and we can directly test whether these are compatible with the actual observations. We can extend such analyses to more clusters in the nearby universe. And in particular, we studied 14 of the most massive clusters in radius less than 200 megaparsecs around us. What you can see here in the panel is basically for these 14 known clusters in the bluish-greenish histograms, that's our posterior mass distributions from the field-level inference approach. And in the symbols, what you can see here are reported literature results on the masses for these clusters. This is very relevant. First of all, we can note that the literature results are not necessarily coherent and consistent. They scatter over a broad range. We now have a dynamical mass estimate from the Borg results, which are in agreement with the literature results and provide very constrained and well-defined posterior distributions. So instead of just relying on statistical summaries as reported before, we can now move beyond this and really also conclusively study cosmology with individual structures and such as the cluster masses, and ask the question whether the abundance of high mass clusters in the nearby universe is consistent with the expectations of a lambda CDM model. And we can say that this is the case for the nearby universe. The field-level inference approach using a physics-forward model allows us also to get a high degree of detail of dynamic information. What I'm showing you here in the slide is the radial peculiar velocity. And in particular, I'm zooming in onto the Perseus cluster around us. And just to show you the degree, detail, and velocity that we can actually get. So we get a large variety and very rich information on the dynamics of our nearby universe that is very relevant for questions on how, for instance, peculiar velocities can impact distance measurements. We have run a large comparison project of the field-level inference projects done with Borg in comparison to state-of-the-art velocity field reconstructions for different data sets. And we have then performed a base factor comparison with respect to the Carrick et al. 2015, which is a gold standard velocity field model used for all kinds of distance tracer analyses, and so on. So a K factor is basically, so a larger value is basically showing an improvement over the Carrick et al. 2015 velocity field. And what we can basically see here is that our reconstructions, which we did in 2024, and our current reconstructions are improving upon the Carrick et al. velocity field, not only by a bit, but by orders of magnitude in these Bayes factor comparison on actually a variety of different distance tracer velocity data sets like the laws, the foundations, and cosmic flows for data sets. This is relevant because this allows us basically to test the impact of peculiar velocities in the nearby universe and the derived cosmological implications from that. One particular interesting object that has been raised recently by Dan Skolnick and is that we can now use individual structures that are well defined, like the coma cluster, to test the distances and maybe get independent ideas on the H0 tangent. The interesting thing is that we have more than 30 years of distance tracer data. We have just plotted them all here. These are the distance tracer information for different kinds of distance traces. The shoes, Cepheids, and supernova 1A data is here, and the combination of all these things have been presented by Dan Skolnick is here. I just want to put in relation our Manticore results, which are here, which are in between the results obtained by Dan in the local universe and the actual Planck distance estimates where coma cluster should be if we had the correct distances, if we would assume the Planck cosmology. So we see that it's in between those two results. It cannot really resolve the observed tangents, but it's important that the Manticore results use a purely dynamic reconstruction method to put coma cluster consistently within the large-scale structure at that point. It's very interesting to note that now through these structure analysis, we can say that it's very challenging to resolve these tensions by pure dynamics for the coma cluster, because the coma cluster is sitting in a very quiet environment. Thus, there is nothing along the line of sight that could accelerate it, for instance, to have higher peculiar velocities that could account for this distance mismatch to the coma cluster that we have. So it remains an issue, but this is the kind of studies that we can now do, turning individual objects into detailed cosmology probes and investigating these kind of tensions. We can not only do this with a coma cluster, we of course can do these kinds of analyses with all kinds of the known structures that we have, for which we now have very detailed position and velocity information. And just to show you here, we basically have the Hubble diagrams for all these clusters, and in different colors we have the posterior distributions of our field level inference, just to show the degree of detail that we can recover. And we also compare our posterior inferences with the actually observed positions on the Hubble diagram for these clusters, and they and these are the results. Another important thing in the nearby universe is the question on the bulk flow and the question on its potentially unusually very large scale amplitudes. So we can use our reconstructions to also look into how the meta distribution is accelerating the observer, or in which direction bulk flows are going, and if they are aligning with the expectations. And what we are showing here in the upper panel, these are the bulk flow measurements as a function of distance, actually. And in the blue boxes, we have the directions and magnitudes for the CMB local group directions. And you can see that the Manticore results actually agree with the bulk flow that is observed also by Carrick et al. To a large degree, which means we can dynamically account for these bulk flow and dipole in the nearby universe with the large-scale structure that we have been recovering and reconstructing. I want to show you that field level inference allows us to look a little bit deeper. Instead of just looking at the large-scale structure at the larger surroundings, what we did here is a work by Ewout Wempe, who was interested in seeing if we can actually extend the data models of field level inference to reconstruct individual galaxies or galaxy pairs, and in particular reconstructing the local group by focusing on the Milky Way and Andromeda pair and trying to reconstruct its formation history. So this is interesting because this provides us with a unique laboratory for galaxy formation dynamics and cosmology in the very nearby universe, but it's very challenging to do these kinds of reconstructions because we need to have a huge dynamic range to cover the large-scale structure in which the local group is embedded and resolve the dynamics. So what Ewout did is he used basically data from mass traces of Milky Way and Andromeda. We have about 40 galaxies and their velocities around us, and the data set is illustrated here. So we can use these kind of data to do a field level inference, focusing directly on the local group analysis with a zoom-in technology. So the zoom-in technology allows us to account for the large-scale structure surrounding the Milky Way, and then we can zoom in into the inner 10 megaparsecs where we resolve the large-scale structures through inference at a higher resolution, and we can see that we recover the Milky Way and Andromeda pair here. So we roughly have an entire box of 40 megaparsecs with a high resolution inner region of 10 megaparsecs, and we have a rough resolution of 78 kiloparsecs. This is a fully differentiable zoom-in model that allows us to use the field level inference approach in the Hamiltonian Monte Carlo setup and allows us to provide a full posterior distribution for these kinds of inferences. And what I'm going to show you here is basically just 5 panels of alternative but plausible large-scale structure formation histories for the Milky Way and Andromeda pair, which you can start seeing forming here. These are 5 plausible but alternative formation histories, all acceptable under the observed data. So you see that we get a full posterior distribution, not only about the individual density fields, but actually over the full 4-dimensional formation history of the local group, and it allows us to do very detailed analyses of the cosmic large-scale structure. We can also provide posterior distributions for all kinds of quantities of the Milky Way and Andromeda pair. We can measure the relative positions, we can measure masses, and so on, and we can then provide you with all these kinds of measurements. One of my particular favorites is that we can look at recovering the rotation curves for Milky Way and Andromeda, and in the blue line and the light blue shaded region, that's our reconstruction from Borg. And in these data points here, these are observations that have been measured from literature. And what you can nicely see is that our data constrained reconstruction nicely recovers the rotation curves of Milky Way and Andromeda consistent with data, which is obviously very interesting and allows lots of opportunity for future analyses and shows you the degree of detail that we are ultimately aiming at in field level inference. There's some immediate results that we get out of that. There's improved mass estimates for Milky Way and Andromeda. These largely align with the Gaia DR2 proper motion observations for the Milky Way. Some key findings are that we have a slightly smaller local group mass that is in comparison to the previous models, which is basically based on the timing argument that you assume the Milky Way Andromeda pair to be just a two-particle system, and then you use that to estimate the masses of the joint system, but that largely ignores the impact of the environment, in particular the quiet Hubble flow surrounding us. And this has a large impact, and the account for the actual large-scale structure in which the Milky Way and Andromeda are embedded has a significant impact on their masses and their dynamical behavior. So what we can see here is we can actually follow the formation histories of Milky Way and Andromeda. And because I'm running out of time, I'm just very briefly telling you, we can basically see, and I'm going back, that initially we are just collapsing along the z-axis into the local sheet. And then once it's collapsed along the local sheet, we see that it starts collapsing within the local sheet. So this is a very interesting dynamics test and understanding from a purely dynamical point of view how the Milky Way basically formed in this local sheet. We can study a lot of things from these reconstructions, like mass assembly histories. We can see if the growth is anisotropic, and we can look in very lots of details of these particular things. In particular, in comparison to just standard simulations, we often figure that in our reconstructions, the Milky Way forms a little bit earlier and grows more slowly than in comparison of a random simulation. And that's owed to the particular environment that we have. So we can basically look at these formation histories of the Milky Way and Andromeda pair, and we can have a very detailed information about this. What I wanted to show you here today is basically that with field level inference, we can advance cosmological inference significantly beyond the current state of the art. So field level inference basically aims at modeling the 3D cosmic structures, not only statistically, but mechanistically, so that we basically also have an actual causal model for how these individual structures in 3D came into being. This allows us to extract all information on cosmic structure from data optimally, and we have shown that using the data in such a way improves cosmological parameter constraints up to 5-fold. We have also shown that beyond the classical cosmology tasks that we can address with that, it allows us to do a variety of interesting new things. So we can build universe models that mirror the actual universe in as much detail as possible. So we get 3D cosmic structures, we get their formation history and the dynamics. It provides us with very accurate mass estimates and velocity estimates that we need to estimate the dynamics, the impact of gravity, and the peculiar realization impact on cosmological parameters, in particular in testing the nearby universe. And it also opens up opportunities for enabling precise cosmology tests with individual objects, such as the COMA cluster. But in more general, it allows us to turn the nearby universe into a physics laboratory for galaxy formation, but also fundamental physics, like testing the decay and annihilation of dark matter, the imprint of massive neutrinos, and other impacts of physics on the particular realization of the large-scale structure. This allows us to advance cosmological inference significantly beyond the current state of the art and gain new insights. So highly nonlinear inference is now becoming numerically feasible. The main challenges still rely on the actual formulation of the data model, in particularly accounting for nonlinear galaxy biasing model. And we hope that as we go to finite, more detailed modeling, this will be an iterative process by understanding data and models to a higher degree of sophistication to explain the data. And we believe that machine learning may enable a much more complex data model than we are currently able to handle. At that point, I would like to thank you for your attention, and I look forward to your questions.